Right, well, that's enough of that. Thank you very much. So, good morning, everyone. Well, it's morning here, wherever you are. I hope you're well, and welcome to today's webinar. So, we are transmitting on with Eventbrite and with LinkedIn and YouTube and Facebook and Twitter. And if you are on any of those platforms, do feel free to message me or ask questions. And in the chat, I've already put some links to mostly free resources. There's one discounted course there, but we'll talk about that later. So what I'm going to do is share a screen with you. Here we go. Yes, it just needs a bit of help. And I'm going to move to, here we go. So what we're going to talk about today is how to identify and analyze functional hazards. And by functional hazards, I mean where typically a computer system, some kind of programmable electronic control system, is controlling effectors, so sensors or some kind of movement or vehicle, or it's presenting safety-related information to humans who then make a decision that may have safety consequences. So this is the third of my current series of free webinars from the Safety Artisan, which I hope you are enjoying. Okay, so a quick word about myself. I've been in the business of system safety for about 25 years now, and I've worked on a wide variety of systems. So lots of aircraft, ships, submarines, air traffic management systems, trains and software, a little bit on vehicles and trains, I should say. And I've worked on some really small programs, which has been lovely, to some ginormous programs, including Eurofighter and Future Submarine, both of which were, slated to be tens of billions of dollars. And the observant amongst you will have noticed that the Australian Future Submarine program failed. So I've got the scar tissue to show for that from other things. And it's from those experiences that I can share with you what works and often what doesn't work. And I've lived in Australia now for just over 10 years and worked here. And before that, I had a full career in the UK. And I've worked on a lot of US and European programs. So I've seen a great variety of ways of doing things, okay? And there's no right or wrong way to do safety. Different nations do it in different ways. Different cultures do it in different ways. But it's understanding, what's appropriate to do in that situation. And I've also had the privilege of teaching hundreds of people in the classroom and thousands online. And I've also been lucky enough to present on safety topics at several international conferences. And I'm just going to go back and double check because can I just make sure, can you all hear me? Can somebody send me a message in the chat? Or if you are on Eventbrite, you'll be able to send me a private chat message, and that's how we will do the question and answer session at the end. So can somebody just confirm that you can hear me okay? Thank you, Carly. Thank you very much. And thank you, Enda. Terrific. Thank you very much. So that's good, because I did do one webinar where the sound didn't work, and I didn't realize until we got to the Q&A session at the end. So that was very annoying, as you can imagine. Right, let's go back. Okay, that's enough about me. So we'll get on to our topic about how do we identify and analyze functional hazards, which is I've seen in a lot of programs, we're great at doing the physical, not so good at the functional. In fact, that's spookily enough, that's where we go on our next slide. So when I talk about physical and functional hazards, the physical stuff, I think we're probably all very familiar with. Generally speaking, it's all to do with energy and toxicity. So with energy, it might be fire, it might be electric shock, it might be falls, so potential energy, so the potential energy of something or someone at height falling, or the impact, the kinetic energy. And then, of course, in terms of toxicity, we've got hazardous chemicals, which are by far the biggest issue that we have to deal with in that sphere. And then we've got sort of biological, plus, of course, sort of smoke and toxic gases, often from fires, okay, or chemical reactions. So those are your physical hazards. And as I said, we tend to be really good at dealing with those. And we're used to dealing with that stuff. And most projects I've been on have been pretty good at identifying and analysing that stuff. Not so for functional hazards. Okay, I've been on lots of projects still today where functional hazards are just ignored completely, or they're only dealt with partially. So let's explain what I mean about functional hazards. So what we're talking about is where a system is required to do something to perform some hazard. So cars move, okay, they start, they move, and they stop, hopefully. But what happens when those functions go wrong? So what happens where we don't get the function when we need it? So the brakes fail on your car, for example. And so that's a fairly obvious one. And if functional hazards are looked at, it's usually the functional failures that get attention. Okay. But they tend to be the obvious failure modes. The less obvious failure modes, and therefore more dangerous, are the other two. So what happens if things work when they shouldn't? So what if you're driving along on a road or the motorway, perhaps at high speed, and all of a sudden your brakes slam on for no apparent reason, and maybe you've got somebody behind you? You know, do you have a collision, or do you lose control on the road and crash? So that works when it shouldn't. Or what if the function works, but it works incorrectly? So, for example, I don't know, you turn the temperature down on something, but instead it goes up, or you steer to the left, but instead your vehicle goes to the right, or it displays wrong information. So if you're in a plane, maybe you've got an altimeter that tells you how high you are. Maybe what would be dangerous if the altimeter told you that you were level in height, or you were climbing, but you were actually descending towards the ground. Okay, and yeah, we've had lots of those kind of accidents. Or you just get you've been told that the wrong engine has failed, which is what happened with the Kegworth Boeing 737 crash years ago now. So there's an overview of what I mean by physical and functional hazards. Okay, and it's important that we're clear on that. So how do we deal with functional hazards? Well, we start by looking at our requirements, and we might do what's called system requirements hazard analysis, which I talked about in another session. And so system requirements hazard analysis is a particular task in MIL Standard 882, but you will do similar work in most standards. Okay. So what we might do is we might look at all of our customer requirements, and we might perform a functional failure analysis. Okay, so we might do that analysis where we do, okay, what happens if it fails to function, functions were not required, or functions incorrectly. Okay, and as the picture on the right shows, I did a run through of how to do an FFA. I think it was at the last, yes, it was at the last webinar in April. And in the chat is a link to that video. So you can see me running through a very, very simplified FFA. So you can see what's happening there. There's also some information on how to do an FFA in the Preliminary Hazard Identification and Analysis Guide, the PHIA guide, which is also one of the freebies, and you can there's a link to that in the chat, okay, and I will send it to you afterwards as well. So what we can do with the functional failure analysis is we can identify those functions that could be hazardous if they went wrong, okay. Although saying that, functions can be hazardous even when they're working correctly in certain circumstances, and that's where we need to think outside the box and look at the context of what might go wrong. But this analysis will help us to do that by helping us to think in a structured way about what we're asking the system to do and what could possibly go wrong. Now, analyzing customer requirements will also do other things for us. Often the customer gives us, whoever they may be, says, you know, I want this, that, and the other. They want certain hazard or risk safety controls put in place, or they put certain regulatory requirements on us and say, you know, I've got to certify, or you've got to certify this product to whatever. So there will be some things in there where they identify specific hazard controls and also some big requirements that need further unpacking. And again, I talked about all of this in the previous session, okay, which you can get from the website. Going through the requirements is a very valuable exercise, and again, it's not something that is always done very well, okay. It's not something that's always done very thoroughly, and I spent quite a lot of time talking about that on the previous webinar. So let's move on. So once we've identified some potential hazards from our FFA, we then need to think about how software or programmable electronic systems might contribute to those hazards. And on the right there, we've got a little model which just illustrates that in isolation, software, programmable stuff can't hurt anybody. Okay, it has a logical state, but no physical being. Okay, so the software has some internal state, it's got some data and variables, and it sees some external inputs, it does some processing, puts them together, and it generates some kind of output to the outside world. And it's at that point, when we get to the outside world, that the hazard occurs or may occur. So either it's telling an actuator or a control system or a vehicle or something, a piece of machinery, to do something potentially hazardous, or it's given a human being wrong information or misleading information that could induce the human to into what we call erroneous human behavior, doing something dangerous, like running out of tea midway through your webinar. That's very risky. Now, it doesn't end there. Just because the hazard is present doesn't mean that we necessarily get an accident. So very often with these functional hazards, this failure or this misleading information must propagate in order to lead to an accident. So maybe it's generated, maybe a component has generated incorrect information, or it gets passed on to the equipment which the component is in, the subsystem maybe which the equipment is in, the subsystem is in the system is in a platform, the platform is in an environment in the real world. And so the problem has got to propagate all the way through these layers to the real world in order to generate an accident, to actually hurt somebody, okay, to interact with a human. And that means that there's lots of opportunities to stop these things becoming an accident, even though the hazard is present, okay, which are external to the software, okay, and we'll come back to that. So we're not just limited often to controlling the software and making sure it doesn't go wrong, but we also need to do hazard control, putting controls in the outside world, okay? And indeed, it's that big system context, understanding that, which will also help us to prevent accidents, even when the software is working correctly. So, for example, there are lots and lots of accidents where the computers on the plane or the ship or the car or whatever it might be, the piece of machinery, were working exactly as they should have been, and an accident still happened. very often because a human misunderstood how the system worked. Okay, and these are very common fatal and catastrophic type accidents. So it's both an opportunity to prevent accidents, and it's something we need to do. Okay, we must always look at software in context, because as I say, on its own, software can't hurt anybody. It's all about the context. And I think on the left, I've said what I've just said, but in a few bullet points. So we need to think about what could go wrong. What are the causes and consequences? Let's understand the whole accident sequence. Let's identify effective controls, not just in the software, but right through the sequence. And let's understand either how software could cause a hazard, or if we're using software to control hazards, how dependable, how much reliance are we placing on that software? In other words, how dependable do we need the software to be? This is the key answer that we must come up with. Okay, what reliance are we placing on the software? And different standards do it in different ways. So if we compare some different approaches, so on the left there we have a model of functional safety, and this is the kind of model that underpins most, well, in fact all functional safety standards. So that's IEC 61508 family. Okay, so we might have ISO 26262, the automotive functional safety standard. That's part of the family. So are the Senelec rail standards, the EN 551 to 6789 series, 61511, which is safety instrumentation. Anyway, there's a ton of functional safety standards. They're all based on this model. So the idea in this model is that you have a level of risk with a system, and we assume that the system already has a basic control system. You know, the car's got a steering wheel or whatever it might be. The chemical plant has some controls, but we've got an uncontrolled level of risk which is too high. Okay, and we want to reduce it. So the model factors in other risk reduction. So those are the external things that we can put in. You know, we can put in pressure relief valves on a chemical plant or stuff like that. We can do other stuff to stop it blowing up, but there's still an unacceptable level of risk. So we've identified all these hazards, and from those we've identified what they call safety instrumented functions, or SIFs, and we need to make the probability of those SIFs, we need to reduce it. Okay, so we need a protection system, and so depending on what safety integrity level, okay, we're going to get a certain benefit from those protection functions. So how much do we need? So the standard says we'll set a tolerable level of risk, and therefore we need to, that will help us to understand which kind of system that we need. So, and usually the SILs go from 1 to 4, where 1 is the least effective and 4 is the most effective. So as you can see in this diagram, in this supposed system, we need a SIL 2 system to get us under the tolerable level of risk. Okay, SIL 1 isn't good enough. And that is, that's the model you get in functional safety. So you will do a sequence of tasks to get you there. You know, you'll identify your hazards, you'll identify your safety functions. You'll typically do a level of protection analysis, a LOPA, L-O-P-A, and you can use event trees and other things to do that. And then from that, you'll have identified all the other factors that you've got reducing the risk, and then you'll end up with a gap between where you are and where you want to be, and that determines the integrity of the protection system that you need. Okay, so that's how that family of standards does it. Okay, in the aviation world, which is the one I'm most used to, typically you will see in military systems, you'll see MIL standard 882 used as the system safety standard, and then we might turn to DO178, the Civil Avionics and Software Development Standard, to say, okay, here's how we're going to develop the software to the required assurance level. And how might we determine the assurance level? Okay, well, we might use typically fault trees, and this is you'll often see enormous quantitative fault trees in the air world. And I mean, here's a very simple example. I've got no light in the room, but imagine one of those things at the bottom, no voltage in the network. Maybe that was caused by a software failure. So we can look at the fault tree and we can say, okay, no voltage in the network. Okay, well, that's an OR gate there. So if that happens, it will go straight to the top event, except yeah, in fact, so it'll go straight to the top event, won't it, in that model? I should have picked, like, on the other hand, if I picked lamp 1 and said lamp 1 was software controlled, lamp 2 would have to fail as well before we had no lights, okay? So that would be better, wouldn't it? We've got an independent system. If the software fails, there's still something else that keeps the lights on, quite literally. So that's the situation we want, where we don't have software failures propagating straight to the top event, straight to the hazard. Okay. Anyway, that's just an illustration of different ways of doing it. Different standards do it in different ways. As I say, I'm talking about a couple of tasks in MIL Standard 882, but you will see similar things in lots of different standards. So just keeping an eye on the time. Now, the way that 882 allocates software assurance or software integrity requirements, it does it in a particular way. Okay, so we'll just run through this briefly to illustrate. So it starts off saying, well, what is the control category of the software you're considering? And at one end, at the top, we've got autonomous control. So the software is in total control, and if it goes wrong, there's no time to save to prevent the accident. Okay, so we are totally reliant on the software. So something like the software in the flight control system of a naturally unstable aircraft. Okay, if we lose the software, we've got nowhere else to go but, well, into the ground. Then at the other end of the scale, we've got no safety impact. So it doesn't matter what the software does, there can never be a hazard. Okay, so those are the sort of black and white extremes, and they're quite easy to work out. Then we've got 3 in the middle. So let's start at the top. We've got semi-autonomous. So the software is in control, or it's providing safety-related information. But if it goes wrong, there is time for outside intervention. Okay, but we're relying on outside intervention to spot that the software has gone wrong and do something about it. Okay, so we're placing quite a lot of reliance on the software. Okay, then preferable to that is redundant fault tolerant. So software control or software safety information is present, software generated safety information is present, but there are also multiple independent safety controls that are always there. Okay, so that's better than SAT, safer. And then finally, in that group of 3 in the middle, there's influential. Okay, so the software might tell us something misleading, or it might do something potentially hazardous, but we don't need the operator to intervene in order to prevent the accident. Okay, so there's some situation there. Maybe if the software fails, whatever it is controlling just naturally settles down into its own natural stability, and there won't be an accident. Okay, the thing might not be as efficient, and maybe that's why we wanted the software to do clever stuff, but it'll settle down to a sort of a basic functionality that isn't hazardous. So there's our 5 levels of SCC, and actually I've spent some time talking about that because that's the most difficult bit to do. Okay, once we've done that well, the rest is fairly easy. The other thing we need to consider, as we've worked out the SCC, and that's the column on the left, is we need to work out, okay, what severity of accident could the software contribute to? Everything from catastrophic, which in 882, that's 1 death, right through to critical, which is one or more severe injuries, and then marginal and negligible. So we combine the two together, and clearly, if we're totally reliant on the software and the result is possibly killing people, then that's the worst case. So that is Software Criticality Index, or SWCI 1. Okay, and it goes from SWCI 1 to SWCI 5. Okay, right down to nothing at all can go wrong. So we put those two together, we work out what the SWCI is, and please note there is no consideration of probability here. Okay, we do not consider probability the way this standard does it, which is totally different to the way that the IEC 6158 family of standards do it. That's all about probability and failure rates. Okay, so but the approach that the ATEC2 takes does not take probability into account, only the architecture of the system and the possible severity of the accident. Now, what that results in is a thing in the ATEC2 that it calls level of rigor. So basically, level of rigor is how much trouble am I going to go to in order to generate software of sufficient quality and dependability that I can use it. And at the bottom, okay, if it's SWCI 5, doesn't relate to safety, we don't need any specific level of rigor, all the way up to SWCI 1, where we've got to analyze everything. We've got to perform safety analysis of requirements, architecture, design, and code, and we've got to conduct in-depth safety-specific testing. Now, this is an old-ish American standard, so it's all about testing. Okay, it's very heavily reliant on testing, as is the DO178 software standard, which is often linked with ATEC2. We might also use, in the military world, we might use the JSSSEH, which is on the Joint System Safety Software Engineering Handbook. Okay, the JSSSEH. So that's that's freely available. You can download that off different sites, plus also guides on how to use it. So there's a whole bunch of rules in there about what you've got to do to your software to meet these different SWCIs, these different levels of rigor. But we can use any software standard. Okay, so we could use MISRA, which is the motor vehicle one. We could use that for to generate the software, or 6158 family, and they talk about SILs, safety integrity levels. We could use, if it's a vehicle, we could use the ISO 26262, and that talks about ASILs, or automotive SILs, or indeed we could use the current version of DO178, which talks about DALs, their development assurance levels. But they all mean the same thing. It's the level of rigor that we're applying to the software development. Okay, now here's a slide. We don't often talk about this. What happens if we can't or don't achieve the required level of rigor? And this is something we never talk about. It's kind of the sort of the dirty little secret in software safety engineering, because nobody wants to admit that we fail or just muck things up totally, which does happen. So what do we do if we don't get there? Well, there's various options. In the 882 standard, you are allowed a senior manager, and the worse the risk, the higher up the chain you have to go. A senior manager is allowed to authorize the risk, even if your software isn't up to snuff. Okay, even if it's not good enough. Now, that is rare. Most standards just don't allow that. If you, in all other standards that I've seen, if you don't achieve the required level of integrity or dependability, you've either got to go back and do it again, or you've got to find some other way of getting there. So maybe you have more external controls or better controls, or maybe you put operational limitations in place to say, don't go to this part of the performance envelope because the software falls over here, or it doesn't work very well, or it doesn't work fast enough maybe. So most standards don't give you this get out of jail free card. And I have to say, I'm not that keen on this myself, but there it is. And it's worth noting that there are legally there are different frameworks that drive us to different behaviors. So in the US, when it comes to failure of a product that can hurt people, probably whoever developed the thing is subject to strict liability. Okay, so there's different kinds of liability in US law, but strict liability is the one that is probably, I'm not a lawyer, but if we look online, we're told when it comes to failure of products that could hurt people, strict liability is probably relevant. And the only defense to strict liability, I am told, is to prove due diligence. So we've got to prove we were diligent in developing the product. Now, if we knew that there was a shortcoming in our software and we went ahead and fielded the system anyway, I think it might be difficult to prove to come up with a due diligence defense unless we could show really, really well with a lot of confidence that the deviations of substandard software couldn't possibly hurt somebody. But then again, if it couldn't possibly hurt somebody, we wouldn't be having this conversation, would we? Then in other jurisdictions, in the UK and Australia, for example, we have to declare that risks are reduced so far as is reasonably practicable, or as low as reasonably practicable. And that test allows us to make a kind of trade-off of safety versus cost, but it's a weighted trade-off in favor of safety, okay? And it's done in different ways. It can be done in a qualitative sense. We can follow a process that puts some rigor into this decision, or we can follow a tolerability approach where we've got numbers, where we've got probability, and then we can look at that. Okay, so again, I have lessons on how to do SFARP, but I'm not going to do that here because that's a whole, that's a whole big thing in itself. And then tolerability is a whole other thing that we've got to understand as well if we're going to go down the trade-off route. So there's different ways of handling, we don't have a perfect system. Okay, let's put it that way. Okay, so I've talked for about almost 40 minutes now. So I'm going to let you know what do you do next. Okay, we've had a brief overview of identifying and analysing functional hazards and how typical standards go about dealing with it. What's next? So what I put in the chat are these links. So first of all, you've got a free PHIA guide. You've also got in the links, you can sign up for subscribe for free emails with more content and discounts by following the link. There's also, I did a foundations course, which talks about the very early stages of system safety programs. And there's a 60% discount on there. It says 1 week. I'll check the date on that. I might have to, I think the date it runs until tomorrow. Okay. But I'll look at extending that. So there's 60% off that course. And also, if you go to the website, there's lots of free content on the blog there. So if you go to safetyartisan.com, there's lots of free stuff on the blogs, and there's paid courses and lessons as well. And in particular, there is, I do a course called Principles of Safe Software Design. And there's a cut down version of that on Udemy, and I've got 500 and something students on that version. That's the cut down version. The full version is on the website only. Okay, so that goes through in much more detail how standards drive us to achieve this required level of rigor, and it gives you some context. I gave you a little bit of context here. We go much more into that and put some figures on the types of accidents that happen, and therefore understanding what we can do about that. So that course is also there. Maybe I'll shove that in the chat as well. I'll find the link to that. So you've got some resources there on the website, and also, as I've mentioned, I do courses on Udemy, which some of which are free, which you can check out. And as it says, go to the website. There's a lot more resources on there. And if you subscribe, you get a series of emails where I share with you excerpts from my most popular videos, so you can see what I do and the way what I teach and the way I teach it, to see if that suits you. Okay, so just remains, before we go to the Q&A session, just remains for me to say that this is a third of a series of 5 webinars, and next we're going to talk about workplace hazard analysis. So we've talked about the very first one, which wasn't last month, that would have been February. We talked about 5 ways to identify hazards. Then in March, we talked about foundations of safety assessment, and I mentioned a little mini course on that. So task 201 is hazard identification. Tasks 202 is preliminary hazard analysis, and 203 is system requirements hazard analysis. I talked about that. Today, we've talked about hazard identification and functional hazard analysis. So that's tasks 201 and 208. Next month, we will talk about 206 and 207. So that is OSHA, that's operating and support hazard analysis, and health hazard analysis. So those are the really important workplace health and safety analysis tasks. And then finally, we will talk about hazard analysis within a systems engineering framework. Okay. And so in there, we're talking about subsystem, system, and system of systems hazard analysis, those 3 tasks there. Okay. And that will be in July. But next month, we're going to be talking about workplace stuff. So I put in some pictures of, people wearing protective gear and doing stuff like welding, and obviously wielding a pen is very, very dangerous in the workplace. Actually, it is. But so we're going to talk about some more typical physical hazards and the work that we do there. Okay, so that will be next month's webinar. Okay, so we're going to move to a Q&A session now. And it says, ask me anything within reason. I'm not very good at questions on sport, okay? But ask me anything either to do with the topics that we've just talked about or safety. So I'm just going to stop sharing there. Okay, so we're still streaming. Now then, I've got a question here already. Hello from various people. It's good to see you. I'm just give me a sec. I'm just gonna pull up. I don't know why I didn't do this earlier. I'm just gonna pull up my website and I will give you a link to that course that I mentioned on safety. So, in fact, okay, right, that's just working away. So do please keep putting questions into the chat and I will get to them. Where are we? Where's it gone? Oh, system safety, risk analysis programs, Australian work health and safety, cyber security. Here we go. Principles of safe software. Right. So I'm just gonna, here we go. I'm just gonna put that in the chat. So here is the link to the principles of safe software course. Right. Okay. So let's start looking at questions. So in the chat, just make sure I haven't missed anything. So yeah, so in the chat at the beginning are all the links to the freebies. So I've got a first question here. Do you start with draft requirements? Presumably a mature requirements document addresses functional failure, at least for an initial design. Okay, well, it varies. If you're lucky enough to get a set of draft requirements from either the customer, the ultimate customer, or the next person up the food chain, then great. You can do some early analysis on that draft, and then you can suggest maybe some changes to the specification to say, well, actually, it would be better if you specified this, not that, or we can't do this, but we can do that. And in fact, that's what a lot of the MIL standard tasks are all about doing that. They're about doing analysis of the requirements to identify the hazards And then you look at it and say, well, actually, ideally, we'd like to eliminate these hazards. So maybe we need to change the requirements so that we can eliminate the hazards, or, it might drive the architecture. So ideally, yes, we'd like that interaction, we'd like that iteration as we take the requirements and do some analysis and make them better. Okay. And in the perfect world, we would have enough time to maybe do that more than once. And in fact, at different levels of the design, as I'm assuming we're going through a sort of a V model, a classic systems engineering, we would be doing that at every level of decomposition as we go down the V towards the code. Okay. But very often we have to start with a customer requirement. So maybe the customer has only given us a concept of operations or a general set of requirements, or maybe they've given us something more detailed. And it doesn't actually matter, even if the customer requirements are rubbish, even if they're really bad, and I've seen lots of really bad requirements, it doesn't really matter too much, because if you do the analysis, you can identify, well, first of all, doing the analysis will help you to identify the bad requirements. And then you can, hopefully you can go back to the customer and say, well, look, this requirement is a bit vague. We can't actually verify it one way or another. So we've come up with a response that's, here's our response to your requirement, and this is something that we can actually verify. Okay, so that's your sort of systems engineering work that should be going on as well in the bigger picture. And as part of that, we can identify hazardous functions. We can identify safety controls. Maybe the customer has given us a prescriptive requirement. Okay, we can go back to the customer and say, do you really mean that? Because maybe this is going to cost you a lot of money and we don't actually think it's necessary. But if they say, yes, no, we want it, then okay, that becomes a safety control or a certification requirement, where we go, okay, how are we going to do a certification program to prove to you that we've met the regulations? So a bit of a long-winded answer, but we need not necessarily have draft requirements. We can still make things, we can still respond to a poor requirement and make it better. Okay. Hopefully before we've signed the contract that says we're going to deliver. Right. So thank you for that. Now, we've got a few people online. Have we got any questions for those in the private chat? Have we got any more? Thank you, Enter, for that response. Have we got any more questions about functional safety and software safety? And you can ask anything you like. If I don't have the answer straight away, I will go and look it up and post it back to everyone, of course. But just let me know if there's anything else you want to ask. So while you have a think about that, I'll tell you what I will do is I'm just going to share with you. I mentioned the website. So here we are. And we've got the sort of the hero bit at the top where we go, I love me. And what you'll see is all of these things along here. These are the free blog posts. So there's a variety of topics, as you can see. So there's the blog post, and I do lessons on system safety assessment and work health and safety. There's some more about why I did stuff, and some people have said nice things. And then if we go to courses, you can see there's some free courses. So we've got Risk Management 101, which is really about the fundamentals of risk management and what the basic terminology means. I did my CISSP, that's cybersecurity course, a couple of years ago. So I did a freebie about how you pass the exam. And then we got some intermediate courses. So we've got system safety risk analysis programs, Australian work health and safety, cybersecurity, and then principles of safe software. And then my biggest course, which covers all 10 of the MIL Standard 882 tasks, is system safety assessment. Now it's $495 US is the full price, but if you sign up for if you register and if you subscribe, you can get a substantial discount on most of these courses, actually. So quick thing. So if you subscribe, or you'll get a pop-up on the website that offers you, okay, you can sign up for free, you get emails, there's no commitment, and you can unsubscribe at any time, okay, and it's all legally compliant, and you'll get discounts on a lot of these courses, and also you'll get to hear, the latest of what I'm doing. Okay, so a little plug there. Let's go back. Do we have right, another question, or two more questions? So I will go to Anoop's question first. Is FFA or FTA the best way to derive functional and technical safety requirements when C logical architecture available? Sorry, is that SEA, Anoop? I'm sorry, I don't understand. Well, anyway, yeah, basically there are lots of different ways to derive these things. If you are doing a level of protection analysis in the 6158 family, the standard will offer you, I think it's 5 or 6 different ways of doing that. But most people use a level of protection analysis, which is in effect an event tree. So it's the kind of the opposite. If you see a bow tie, you imagine you've got a fault tree on the left, which focuses you down to the hazard, and then from the hazard you can use an event tree to develop the different paths to the different consequences that might arise, some of which involve harming people. So there's lots of different techniques for doing it, and it really depends on which standard or which industry you're in. Okay, but if you're starting from scratch, my advice would be start simple, and then if you can't derive a result. So when I say start simple, think about, can you cut software out of the safety loop, or make the software completely non-hazardous? Can you do that ideally? If you can't, then I would recommend looking at external controls wherever possible, because developing safety related software is always going to be challenging. Okay, so it's almost always cheaper and better to reduce the reliance on software wherever you can. Okay, and then you would apply an analysis method that would suit what you're doing. Okay, and that might be a fault tree where you say, okay, I can control things before the hazard, or it might be I've got to control things after the hazard, or both, ideally both. So look at the big picture. Okay, don't get fixated on the software, which is what a lot of people do, and that will help you. If you've already developed your architecture, then you've already made all of those decisions, and you're really stuck with what you've got. So in that case, you're going to have to look at the software itself and consider in detail how software failures or errors might lead to those known hazards, okay, within that architecture. And once you've understood how the software can go wrong, you can define more precisely, engineering development and analysis and tests to make sure that that doesn't happen. Okay, but the more precise your understanding of, this particular, if the software goes into live lock or deadlock, it can cause this. But maybe we've got a hardware watchdog in the processor or externally that goes, oh, the software is frozen, revert to backup control, whatever it might be. Yeah, but it all depends on how defined. If you've defined your architecture already, you've made all of those decisions effectively. So thank you, Anoop. I hope I've answered your question as you wanted me to. So I've got another question over here. Should a good set of requirements list the hazards that have been eliminated through the requirements? Yeah, I would say so. It need not be in the requirements, but you hopefully in the hazard log or somewhere else, we've gone through, we've identified, and this takes us back to the preliminary hazard ID. So we would start with a very broad and shallow hazard identification exercise. So we would identify everything that might possibly go wrong. And then with subsequent analysis, we might refine that and say, okay, we thought this might be a hazard. Actually, it's not credible. So we will close it, but we don't delete it. We leave in the hazard log or the hazard tracking system, we have an audit trail that shows us that we've considered these things and eliminated them or dealt with them in some way, okay, and what we've decided to do about it, okay. So that's how we would do that. Yeah, and the sort of supplementary question to that is, how is traceability from hazards to requirements handled? Okay, so going back the other way, it depends. So if we've identified a requirement that is actually a specific control, then we would just put that requirement straight into the controls bit of the hazard log. Okay, so we should have a list of controls in there. So we go, okay, the customer has said, I don't know, I want you to have a dual redundant braking system on this vehicle. So that goes, so that's a requirement, and it's in the hazard log as a control with the reference to the requirement. And then of course that's great because the systems engineering people will be verifying that requirement, so the safety team doesn't have to bother. Okay, we don't have to generate any specific safety evidence. We just go, okay, when the systems engineering people have verified that requirement has been met, we can tick off that control. No further effort required from us, which is terrific. That's what we want. Otherwise, if you've identified hazards from a requirement, you should have a documented functional failure analysis table, and I show you, I fill in one of those tables in the example. Okay, so go and look at the link for that. And so you will have a tabular record that says these requirements generated these hazards. Okay, so that's how that traceability would work through the analysis into the hazard log again. Okay, and of course, sorry, I didn't say you would be numbering all of, you'll be giving unique ID numbers to all your hazards and all your controls, and if you're doing causes and consequences and other things, you would uniquely number all of them, so you've got traceability. Okay, so some good questions there. Thank you very much. We're out of time. So do we have any more questions before we wrap up? By the way, if you think of a question afterwards, please get in contact. You can message me on Facebook, LinkedIn. Well, yeah, I'm not on Instagram at the moment. Twitter. You can go to the website and ask a question. You can send me an email to admin@safetyartisan.com if you want to ask a question privately. And let me know if there's anything else you want to ask, and I will be happy to help. Okay, all right. Okay, just had a supplementary. So, violation of safety goals. Yeah, that's good. Yeah, if we know what our safety goals are or safety targets, yes, we can use our analysis methods to check for violations. Sorry, so the question I think is, how do failures not violate safety goals? So there's different answers to that. So first of all, software is chock full of errors. There's going to be lots of errors in your software, but most of them will never lead to an accident. Okay, and it's understanding what errors could lead to an accident, what can't, is important. So that's the first thing to say. So there could be lots of failure modes, depending on your architecture and depending on the context, where your system can fail safe naturally, the software can stop working, a human being could take over, a backup system could take over. You can still meet your safety goals. Okay, you've still got a safe system. You've just lost some functionality, and maybe you've lost the availability of the system. You've got some downtime because you've got to fix it, but it hasn't caused an accident. Now, how are those assessed against ASIL? So ASILs in the automotive world. So we're doing the SIL assessment that I discussed with the diagram of achieving the necessary risk reduction. But also A-cells add another thing in where they talk about controllability. So the idea is, if your vehicle goes wrong, can the driver intervene and control the failure and avoid an accident? And sometimes the driver can. So if your safety goals say, okay, I only want the driver to take over, no more than once in, I don't know, 100 driving hours, let's say, you might be able to determine that you've got a failure budget that allows you to achieve that goal. Okay, given the fact that there's some filtering going on with external controls that reduce the probability of that happening. So you could have a probabilistic argument for still meeting your safety goals. You could have an architecture argument because you've got backups, etc. There's different ways you can do it, okay? But it's all about understanding failures in context, remembering that software in isolation cannot hurt anyone. So how does that software-generated hazard propagate to hurt somebody? If you can understand that progression, you can stop it, okay? Hopefully. Right. Okay, everyone. Well, if there's no further questions, thank you very much, everyone, for tuning in. And as I say, if you do have any more questions, then do please get in touch after the webinar, and I will be happy to help. No, you're very welcome. Thank you. Okay, everyone. Well, I'm going to say goodbye and see you then or next month. Okay. Thanks.